And our next speaker and last speaker before the break is Wei Zhang towards self-contained metadata search capability for self-describing file formats.
Hello, everyone. So my name is Wei Zhang, and currently I'm working in Lawrence Berkeley National Lab. So today my topic is towards self-contained metadata search capability for self-describing file formats. So nowadays, scientific applications, including experiments and observations, they are generating ever-increasing amount of data. And all of these data are ever increasing in terms of the size of the files, the number of the files, and the variety of the files. And in many of these scientific applications, they are storing their data in self-describing data formats, including HDF5, netCDF, etc. And so in these self-describing data formats, the metadata is stored alongside the data objects. So that comes to the question where, for example, what if you want to find the particular data objects with the specified data metadata attributes? Then what would you do? And also, oftentimes we want this metadata search capability to be widely available everywhere your data set is. So one possible way is to scan all the files, definitely, but that will be really time consuming due to the sheer size of the data objects and also the number of data files you have. So through the years, we have seen many of the scientific applications that are developing their own techniques for supporting metadata search. They're basically using different kind of databases to support the functionality of metadata search, including like NoSQL or RDBMS. However, when you have a database, the first thing you have to do is to deploy that database first. So there will be definitely some sort of effort you need to do for deploying the database. And also, in order to make sure your database works all the time, you have to maintain your database. And also, when you set up the database, you have to import the metadata that was already inside of the data files to your database. So in that case, you have to transform your metadata into the particular format that your database can accept. And not to mention that is causing some storage redundancy because you're basically duplicating your metadata to another place. And also, since usually the database are running in a dedicated system, so usually the applications would have to access your database through the network, so that would cause performance issues. Not to mention that when you want to, for example, migrate your database to from a HPC facility to another, you would have to in this case, like using a database, it's really poor in terms of the portability and mobility. So what we envision in this work is a new era of metadata search where the metadata indexing is actually stored alongside with the dataset files, so that you can have your application can have direct access to the metadata index. So with the self-contained metadata index, we can reduce the complexity in terms of transforming the metadata schema, and also we can reduce the complexity for building up metadata search process. And also, since the metadata index goes with your data set, definitely it will enhance the portability and mobility of the search capability. And also, what we want is to make sure we have minimal storage footprint that we can easily store the metadata index along with your dataset without costing too much space. And also, definitely, the performance has to be excellent. So with this vision, we actually build up this metadata indexing and querying service where we have an index builder. And it basically went through the entire hierarchy of your dataset all the way through the directory to the file, to the object, and to each single attribute that is attached to the object. And also we have this index file counter in order to make sure that each process in your application will just simply scan part of the data set. And once that is done, each process is going to build their own in-memory index. So we designed this in-memory index with two-level indexing trees. And also for removing the, avoiding the redundancy for storing repetitive file paths and object paths, we basically encoded the file path and object path into different numerical IDs. And so for this two-level indexing tree, we associate the leaf node with the pair of file path identifiers and object path identifiers. So also, in order to be able to store the metadata index actually on the disk, we designed this compact index format. With this, we are able to actually store the in-memory index to disk in a compact way. And also, we designed this indexing file read and write procedure to be able to actually store the file, store all the in-memory index for each process to the disk. And then later on, when the initial indexing is finished, then all the process can follow a retrospective loading process in order to be able to load all of these index files to itself, so that each process will have a full copy of the metadata index. So, and also the retrospective loading process also serves as the indexing recovery procedure. So once you have the in-memory metadata index, you will be able to serve the metadata queries. So for example, for the numerical attribute, you can basically send the query, and then the query will go through the first level adaptive records tree, and then the numerical value will go to the SBST, and then it will just be able to locate the file path identifier and object path identifier. And also for a string attribute value, it follows the same path to be able to actually retrieve the file path ID and object path ID. So we've done extensive evaluation. So we made a comparison between MIQS and MongoDB. So the reason why we choose MongoDB, because first of all, it is a NoSQL database and has a flexible data schema. And it is the state-of-the-art solution in many of the existing domain scientist works. So the data set we have is like 100 HDF5 files that comes from the BOSS data set. And totally the data set size is like 145 gigabytes and with 250 attributes. And we have 144 million key value pairs with 1.5 million data objects. So in terms of the indexing time, for MongoDB, it takes up to 5 to 9 minutes to be able to index all 16 attributes. However, in MIQS, with 16 attributes, we were able to achieve 50% indexing time reduction for an initial indexing process. And for recovering the index, we were able to achieve 99% of the indexing time reduction. And with MIQS, you can also actually index all 250 attributes in MIQS within 8 or 14 minutes. And you will be able to actually recover the index of all 250 attributes within 2 minutes. So that is really quick. You can consider, for example, if you want to reconstruct your index after you migrate your data set, it's going to be really quick to reconstruct your index. And also, this is a breakdown of the indexing time. So as you can see with MongoDB, it spent 3 to 6 minutes for inserting the BSIN document from into MongoDB. But however, for MIQS, it only takes half to 1 minute to be able to actually build up the in-memory index, and also the time for saving it onto disk is really ignorable. Again, for 250 attributes, we spend 5 to 8 minutes, and also still the persistence time is really ignorable. And for recovering your metadata index, it takes less than 40 seconds for 16 attributes, and also it takes less than 2 minutes for all 250 attributes. So speaking of the storage consumption, for 16 attributes, it takes up to 402 gigabytes in MongoDB, and most of the space are spent for storing the BSIN document in MongoDB. However, in MIQS, since we don't have to store, we don't have to duplicate the metadata again, and for storing the index for only 16 attributes, it takes up to 600 megabytes. And for all 250 attributes, it takes up to 7.8 gigabytes. And we were able to achieve 75% of the storage space reduction. And that means with MIQS, you're able to either save a lot of space when indexing the same amount of attributes, or you are able to actually index a lot more attributes with the same amount of memory. So for query performance, we were able to test this with 22 100 parallel processes, and for each process sends 1,000 queries covering all 16 attributes we've indexed. And then for MongoDB, it takes up to 5 minutes for every 1,000 queries on average at the maximum scale. And then for throughput-wise, it was like 319 kilo queries per second at maximum scale. And then, however, for MIQS, it was like up to 0.29 millisecond per 1,000 query at maximum scale. And then it was like 363 billion queries at maximum scale. So we were able to achieve 172 kilo times such performance improvement. I will basically jump over this section. I'm not really sure like how much time do I have. In conclusion, basically in MIQS, we were able to devise a self-contained metadata indexing and querying service, and the basic goal is to make sure that the metadata search capability is widely available with the self-describing tool chains. Like, for example, think about what if HDF5 has this capability just as a native feature for its own, right? And then the benefits is that we have the minimum complexity in terms of managing this metadata search capability, and also we were able to achieve minimal storage footprint, and also the portability and mobility, and thus definitely we have impressive performance. So in terms of future work, definitely we're seeking for integration with various self-describing formats, definitely including HDF5, and it's actually when people talking about like the new features that maybe that comes with HDF5, maybe in the next generation or maybe next year. I think definitely this would be something we should consider, and definitely to support, we would like to support more different types of queries, and for that we need to, for example, investigate like what will be the new types of metadata, and also will be the new representation of the metadata, and also the index, and also for performance improvement. And from a broader perspective, I would say we really have to look into like different types of metadata and how the metadata can be, or how the metadata search can be utilized in terms of, for example, maybe data compression, or for example, like sparse data management, right? And yeah, a lot of cases. So this will be really interesting and really to think about, right? So yeah, that's basically everything. Any questions? Okay. Mm-hmm. So basically, as you can see, actually when we utilize this invariant index, we had this two-level indexing tree structure, and for the adaptive regex tree, basically it's a trie-based approach to be able to store the attribute names. So in that, we actually it naturally actually already did some sort of a compression for the attributes already, or the attribute names already. So not to mention that in the second level adaptive regex tree for storing the string attribute values. Again, there's sort of the compression there, and also for avoiding the repetition of the file paths and object paths. Think about like the deep hierarchy we have in the traditional like HDF5 file, right? So like with this, we were able to avoid the the occurrence of various file paths and object paths. So. Oh yeah. So for this one, actually, I think it would be good to think about, for example, the case when you have a database. As I said, so for a database, at that time for the evaluation, we were like all the drivers were actually talking to the database over the network. So this is basically a dedicated system we set up for the evaluation on MongoDB. So when we have 100 processes and they are sending 1,000 parallel queries altogether through the network to database and to be able to get the actual result, it takes really long time, and it becomes really a very hectic congestion here for the network. So, but with MIQS, we actually every query is like performed inside of each process. So that is the magic of the in-memory index. Yeah. Okay. Yeah.